still discussing the theme, innovation and science for humanity. The reason why they came up with this theme, they say the objective is so that we can have discussion around science for society. And who can we talk to if we don't talk to communicators? And here I have Gillian from NRF-iThemba LABS. But before I even go further, Gillian, can you please introduce yourself and what you do and what does iThemba LABS do?
Well, thanks for the invite. I'm Gillian, based at NRF-iThemba LABS, and of course LABS is an acronym, which is short for the Laboratory for Accelerator-Based Science. So everything that we do relies on the availability of accelerators. And with these accelerators, obviously, we are playing in what we could call the science of the very small and the very fast. So there's this need for us to try and understand things at a fundamental level, trying to understand nature, matter, but there's also a need for us to think about how do we use our knowledge and our skills to impact society. And one of the things that we do is we produce what we call radiopharmaceuticals, and these things are the things that we use in medicine when we want to diagnose and treat cancer. So on the one side, it's fundamental science, trying to understand nature. There's also some applications in terms of material science. And then on the other end, it's really just how do we use our knowledge of the interaction between radiation and biology, for argument's sake, to impact the lives of people through cancer research.
So already, for me, it sounds relatable the way you just introduced it. But my next question was going to be, nuclear physics is really, really hard to break down, especially for the general public. Even if I want to write an article on nuclear physics and I put it to the simple English, is always hard. How do you, as the communicator of this science, make it such that it's so relatable and easy to understand to even primary school level?
Well, I think that's the challenge. I think by nature, we are masters at taking simple things and make it sound complicated. But when it comes to taking the complicated things and making it accessible, that's where the creativity comes in. That's our need to think differently and to sometimes try and find common things to help people understand. But I think for us, it's realizing that even in the word nuclear, I often say what people tend to do is to interchange the first two letters. So nuclear becomes unclear. And people immediately go to bombs. We are building bombs. But people forget about things like X-rays. People forget about things like microwaves. Because these are all applications of, in essence, nuclear science and technology. And I think the challenge is to understand that when I say we talk about the science of the very small and the very fast, we are living in a space where we talk about stuff that you can't see and you can't touch. And the only way for us to get to this world of the invisible is through mathematics. Because now you have to start thinking in an abstract way. And I think the challenge for us in South Africa is to reposition mathematics and science as enablers and not as stumbling blocks. That people focus on what are the skills that I learn through studying the subjects and not be blinded by difficult. Because I think the flip side is, we can try and go the other route by always trying to say, science is cool. Yes, it can be cool for people to understand what it's about, but often it's hard and you need to grind. And if you don't have that almost willingness to keep fighting and to keep pushing, you will get tired. But we don't want everybody to be a scientist. We just want people to have the basic tools to be able to ask critical questions. We want people to remain curious. And when you're curious, you pay attention and you ask questions. And I think when you do those things, in my mind, you're a scientist.
Yeah, true. We had an aha moment the last time you gave a talk in SASTEC conference. And I want to give you the platform now to give an aha moment to anyone who is listening or watching this video right now. You were explaining something, and like everyone in this room, and I remember I was still blinking. I think you said something that when you blink, it said, "Can you please give us another aha moment when you break down nuclear physics to the general public?"
Yeah, so I think, we often say it's the science of the very small. And often when we talk to young people, we talk about atoms, we talk about protons. And when you ask them, so how small is a proton? The answer is very small.
Yes.
But the question is, so how small is small? And I think, in trying to explain our world, what we need to do is to give people a sense of how small is small. So when I talk about a proton, imagine you have a meter length, right? So if you have a meter length and you cut it up into 1,000 pieces, then the smallest piece that you take out would be 1,000th of a meter, but we call that a millimeter, right? And we know what that is. That's a little line on your ruler. But if you now take the millimeter and you cut that up into 1,000 pieces, and you take out one, then that would be 1,000th of a millimeter or 1,000,000th of a meter. We call that a micrometer. And to give the audience a sense of what that is, if you take 50 microns and put it together, that's more or less the thickness of your hair. Right? So your hair is at the order of 50 microns, so I can still see that.
Yes.
But now if you take a micrometer and you cut it up into 1,000 pieces and you take out one, then I'm now at 1,000th of a micrometer. So in mathematics, that is 10 to the minus 9, which we call a nanometer. But wait, there's more. Take the nanometer, cut it up into 1,000 pieces, take out one. Now we are 10 to the minus 12, which is a picometer. But we're not there yet. So I take a picometer, cut it up into 1,000 pieces, take out one, that's a femtometer, and that is the size of a proton. So I basically take a meter length and I subdivide it into 1,000 pieces 5 times, and then I'm at the size of a proton. And now at ITHEMBA, we take this small thing and we put it in a big machine which we call an accelerator. And the accelerator makes it go faster and faster and faster. And the basic science is we use an electric field to give the proton a kick because it's charged, so you can make it go faster. And when it goes faster, we use a magnetic field to change the direction. So the magnetic field bends, but it can't give it more energy, right? So you have this combination of kick and turn, and that is what we call our machine a cyclotron.
Yes.
So put the small thing in our machine, when it gets to maximum energy, it has enough energy to go more or less 4 times around the Earth in 1 second.
Wow.
And 1 second is the time that you take to wink. That is our world.
And that lecture I was busy winking, And then, when you took it to the length of the hair and cut it down, I was still seeing the image. And the more you cut it down, I'm not losing the image. And it gives people the sense of the very small and very fast.
And of course, and that is of course not where it ends, because we are in the world of nuclear physics, but you could go further when you get to particle physics or high energy physics, where you actually have to take the femtometer and cut it up into another 1,000 pieces and get to the 10 to the minus 18. And now you have the building blocks of protons, which we call quarks. But maybe that is for another day.
Wow. This is always exciting when you break it down, because we're still on the science that is impacting the society. Let's talk about the medical isotope production that you guys do at iThemba LABS.
Yeah, so for the general public, ISO means the same.
Okay.
So isotope refers to the fact that you have the same number of protons, right? So in your nucleus, you have the building blocks being protons and neutrons. And if I have a setup where I have the same number of protons, but I have different number of neutrons, I can have what I call an isotope.
Okay.
So for instance, if I take carbon 12, 6 protons, 6 neutrons, but I can also get carbon 14, and that has 6 protons, but 8 neutrons. And because of this imbalance, this element or this particle, the substance, is what we call radioactive. And that is my radiopharmaceutical. So in nature, you get stuff that's naturally radioactive, but we can artificially make stuff radioactive. So we take a target, we bombard it with these projectiles, and in that collision, we create something that's radioactive. And if we know what we're doing, we can convert that into a radiopharmaceutical. Because chemically, there's no difference between carbon 12 and carbon 14. Because they both have 6 protons, they have 6 electrons. So they look the same. So radioactive carbon dioxide is the same as normal carbon dioxide. But the difference is that because the one is radioactive, when it decays, it gives us signals. So in the world of radiopharmaceuticals, in cancer research, if you, for instance, need to be diagnosed, then in principle, I can inject you with a substance that's radioactive, right? And if I tag the radioactive substance to something else, then I can basically follow the radioactive substance. And if you think about cancer, it deals with this uncontrolled growth of cells.
Yes.
And when cells go crazy, they need energy. So if I tag this to energy, let's call it sugar. So the sugar will go where the sugar gets eaten. And if the sugar gets eaten and I have this label there that gives me a signal, then I know where the cancer is. So it's really the sense of using fancy techniques to search for, and based on some activity I find, and if I have a fancy detector, I can locate. And if this cancer obviously is located in a specific space, I can either go and cut it out through surgery, or I could use radiotherapy, or I could use chemotherapy because the cancer spread throughout the body, and then I use chemicals to try and kill the cancer. Right? But I think it's this weird thing where on the one side, radiation causes cancer. But if we know what we're doing, we can use radiation to cure cancer. And I think that's the beauty of the science, it's the beauty of the research. So as we learn, I mean, innovation is finding new ways of doing things. So the more we know, there are opportunities that come about. And there are opportunities that present themselves for us to be able to make an impact. I think that's why it's really important to, even though there's a strong focus on impact, that we don't lose sight of the importance of research for the sake of research. Because we need people who are creative. We need people who search for answers for unanswered questions. And in that pursuit, there might be spin-offs that have got impact and implications in terms of changing society for the better.
Okay. I think right now I'm even more focused on the lecture that I had than the questions that I've drafted. You said something about the production or the technology that you guys are using is 24 hours. When you had to, because I'm asking this because someone can be still saying, but how does it directly impact us? You know, things like that. And you said something about it producing certain hours. It has to be inserted to people certain hours. Also the production that is only with iThemba LABS and is distributing throughout the world. So can you please take us through that?
Yeah, so associated with your radiopharmaceuticals or your isotope, there is something that you call the half-life, right?
Yes.
So the half-life is the time that it takes for the thing that was originally radioactive to reduce by a factor 2. Right? And normally you would say after about 10 half-lives, it is no more. So if you produce something that's got a very short half-life, in other words, in a very short space of time, it reduces. Then after 10 of these cycles, it is no more. Right? So if we produce an isotope with a short half-life, then really you have to produce it. You have to convert it and go through all your quality checks and balances to the point where it becomes a radiopharmaceutical that's ready for intake by a patient. But that means you have to produce, do your quality checks, get this to the hospital and get it in the patient before you've gone through your 10 cycles of decay, because then there's nothing left. So if it is a short half-life isotope, obviously those are the constraints. So if we, for instance, produce something in Cape Town with short half-lives, then we can service the local industry. But similarly, you might have that in Gauteng, there is NTP linked to Nexa, and they might service the northern side. And then if you have stuff that live longer, you can actually export that. So we produce something which we call a generator. So it's almost like a mother and daughter, right? So you make the mother, and then the mother decays into the daughter, and the daughter is what you actually use for the patient. But because the mother takes a bit long to decay, I can export the mother, and as the mother decays to the daughter, which is short-lived, I'm then at the hospital to give that to the patient. So again, it's coming up with innovative ways to address the challenge, especially when it gets to you're more shorter lived. And then, as you mentioned, iThemba LABS is the only facility that produces an isotope known as sodium-22, and that does not have a medical application, so it's more a research isotope, but we are the only producers of that specific isotope in the world. Yeah.
My next question is, what trends and challenges do you see shaping the future of nuclear science in the next decades?
Well, I think if you think in terms of, the diagnosis process, so if you use isotopes, you always need, let's call it, fancy eyes, right? So it's the interplay between, there's something that I use to tag, there's something that gives me the signal, but I need a fancy camera to be able to see. So at the moment, your body, your scanners are expensive technology.
Yeah.
So I think one of the drives would be to find innovative ways to produce systems that allow us to detect the radiation, but that is not as expensive, and that we can actually roll out to all parts of the country. Because on the one side, we would be able to say, we can up our production. We actually are bringing a dedicated machine online so that we can increase our production yield. But even though we increase the yield, you still need the fancy equipment for people to be able to use it. So I think the drive would be to either find new ways of detection that allows hospitals and institutions to be able to use the technology. But there's also a way for us to start investing in other isotopes. Okay. So some of the buzzwords at the moment is this idea of theranostics, where thera refers to the therapy, and the gnostics refers to the diagnosis. So it's almost having, two friends hunting in unison. The one you use to find, and once you find, you treat.
Okay.
So that's the theranostic. So there's a diagnostic isotope that I use to find, but there's a therapeutic isotope that tags along. So as you find, I kill. Yes. Because in a sense, you try and impact the impact of the radiation. And the ideal is to basically deposit the energy in the tumor while ensuring that you limit the exposure of the healthy tissue. Wow. So you need to find innovative ways of saying, we need to find better and make sure that we only impact where we need to impact, and therefore we stay away from the healthy tissue. So I think it's advances in the detection, it's advances maybe in terms of new isotopes. One of the things that we are thinking about is exotic radioactive beams, right? So in order to produce the isotope, you use a projectile and a target. But if your projectile itself is radioactive, then you might be able to produce a new suite of radioisotopes, because you can start getting into a different part of your chart of radionuclides, which open a new world in terms of what the capabilities are. So there's a lot of things happening, but ultimately we're going to need people. And we need young people who are willing to take on the challenge, who are willing to say, how do I use my skills, my talents? Some of them might be keen on the actual science, but some of them might be more keen on the technology side, right? Because we're in a radiation space, so there's need for programmers, computer scientists, AI, machine learning is the new thing. So how can we train our machines so that we become more efficient? So there's a whole myriad of opportunities. And again, I think it is just us being able to say, within a science space, it's about being creative. So let's continue to ask questions, and who knows, maybe there'll be some amazing things waiting just around the corner.
You make me wonder the way you communicate science. Are you a scientist? Are you doing the science, or you just translating the science and you communicate it like?
Well, I don't know, maybe I should call myself a detribalized scientist. I formally studied science. Okay. So I've got a PhD in experimental nuclear physics, but that's many moons ago. Okay. And I think over the years, because I spent a lot of time in academia as a lecturer, that is where you probably develop a little bit of your communication skill. Okay. Then I spent many years in outreach, science awareness, and maybe there it was honed. Then I spent some years in student support, student recruitment, bit of marketing. So I think if I add it all together, maybe over the years I've been shaped into something that looks a bit different.
Yeah.
And also being able to challenge this perception that, you know, scientists don't have personalities. To say that, listen, we are normal people, and we're not just people who use our bodies to move our heads around. We also have other interests. Okay. And it's allowing people to tap into their own strengths and to marry the world in terms of what it is that we want to do to, at the end of the day, through conversations, impact the lives of other people.
Okay. Touching on outreach, what do you tell those young people when you tell them to pursue careers in nuclear physics? What is the strategy? What are you telling them? Like, you know, I'm saying this because in astronomy, when they recruit, are like, where am I going to work? So how do you do it in nuclear physics?
Well, I think with many things, we are maybe currently in a space where people want almost like immediate feedback, or people want the immediate sense of where this is going. And sometimes we need to understand that we're on a journey. So I think within the country, in terms of education, there's a need for us to move away from education being performance driven.
Okay.
And it's about people being able to explore, you know, what are the things that I enjoy? What are the things that I'm good at? But ultimately, I have to start asking myself, what is it that the world needs?
Yes.
And how am I able to serve the world, given my skills, given my knowledge? And I think often we end up limiting the people at such a young age because we want to put them in a box and say, oh, you're going to be a scientist.
Yeah.
And actually, you know, I'm currently working as a communicator, right? With a science background. But I never studied marketing. And my life journey allowed me to become what I'm currently doing.
Yes.
And I think we have to find a way to keep that door open for young people. I think there are too many people who are sitting at home maybe saying, oh, I am a graduate, but I'm unemployed.
Yes.
And the question is, why are you unemployed? You're probably unemployed because you are focusing on your content knowledge.
Yes.
And you've not challenged yourself to think about, what is my skill set? And what does the world need that I, because of my meanness, there's only one like me. How can I serve the world, bringing not just my knowledge, but all that I am through my skills?
Yeah. And
I think that is our challenge. So for me, for the young person out there who's thinking about, you know, the possibility, I would just say, you know, maybe the KISS principle. Keep it simple, stupid. Just journey through life and allow opportunities to present themselves to you, and don't get bogged down because you can often limit yourself. You know, I've seen people who, for argument's sake, say, one day I want to be, I don't know, a chartered accountant. And then they get into a conversation of, okay, how much am I going to earn? Where am I going to work? And then even before they have applied to a university to go and study accounting, they decide that this is not for me.
Yeah.
And I think that's crazy. So,
True.
So allow life to teach you. And I think just, you know, keep a growth mindset and know that there's stuff that you don't know. But that's the beauty of the journey, and allow life to take you where life needs to take you.
You highlighted that you want to change the perception of scientists as certain people, so scientists are normal people. So what do you do for fun?
For fun? Oh, a little bit of this, a little bit of that. So I enjoy music. Okay. So I sang in a formal choir for something like 17 years. And again, singing in a choir, it's connecting with audiences. So doing solo work, you know, not that I say I can sing, but yeah, so I sing. I'm active at church. I play one string on my bass guitar. I can play 3 notes on the piano. And sometimes I say, oh, that's not enough. But if I compare myself to the average person who can't play piano, maybe I need to claim that. So a little bit of fun is a bit of music, quiet time. I'm an introvert, so I enjoy reading a book every now and then and just be with myself. At the moment, I'm trying to read a book with the title super communicators.
Cool. That was a very nice conversation, Gillian. Any other additional looking forward to in the Science Forum?
Well, I'm looking forward to learn. I'm especially interested in having conversations with young people.
Okay.
And trying to understand where they are in their thinking, but also trying to understand what are the possible limiting assumptions that they have placed in front of their own growth, because they have become used to other people solving their problems. I think it's time for them to own their space and to say, what is it that I want and how do I make it work for me? So I'm interested in engaging, and I'm interested to explore this notion of social capital. Sure. How do we allow people to sit around a table who normally would not sit around the table? But how do we make them feel welcome and not constantly walk into rooms where we're trying to show other people how clever we are? So I'm eager to learn, and I just want to walk around and see if I can get a sense of that.
Thank you so much, Gillian, for your time. I almost asked you to sing for us your go-to song. We are still at the Science Forum, exploring the theme, igniting conversation and science for humanity.